this lesson, we're going to be taking a look at what we've been using with electron configurations and orbital diagrams and trying to use those to understand how atoms can form ions. I also want to take a quick look at electron dot structures because that will come useful to us when we take a look at drawing bonding diagrams in a later lesson. So we know that in any atom, those electrons in the outermost shell are the ones that do the bonding. The other electrons are buried deep within the atom and aren't really available to other atoms to form bonds. So the valence shell is what we call the outer shell, and we know it's not necessarily the highest energy electrons, they're just the ones furthest from the nucleus. When I go and want to draw a Lewis dot diagram, all I'm drawing is my valence electrons. In the example of chlorine, we have 7 valence electrons. We have 2 in the 3s sublevel, and we have more in the 3p sublevel. So all of 3s and 3p are our electrons that are involved in the valence shell, and these are the ones that might be available for bonding. I can always tell which are my valence electrons because they are the ones with the highest principal quantum number. Because there are 7 valence electrons that we have in chlorine, I draw 7 dots around the chlorine. Now, in the past, what I've taught you to do is to pair up electrons where we can. A good general rule that you can use is to work your way around the clock. So as you're placing electrons around an element, start by spreading them out evenly. And then as we continue to make pairs, as you continue to work your way around the clock. Now, this isn't the only way to draw a Lewis dot diagram, but it is a good general rule to help you figure out the shapes that atoms might be able to make when they form molecules in later lessons. In the case of magnesium, there are only 2 electrons available. In the valence shell, we fill in 3s for 2. So we would draw 2 dots. Again, remember, these are not necessarily the highest energy electrons. For example, if I was to draw gallium, and we think about what we have for gallium, we remember that gallium starts filling in after we've already done all of the inner electrons for argon. Then you would go to 4s for 2, 3d for 10, and then 4p for 1 to make the electron configuration for gallium. Only the ones with the highest principal quantum number, the big number in the front, are valence. 3d10 is a high energy set of electrons, but it isn't valence. So when I go to draw the electron dot for gallium, I have the 2 in the 4s sublevel and 1 in the 4p sublevel. I have 3 valence electrons. So using our understanding of which electrons are valence allows us to figure out how to make ions. And really nothing is new here than it's been that ions we've talked with you about in grades 10 and 11. We're going to follow the octet rule. We're either going to give electrons away, as metals tend to do, or gain electrons in order to reach a full outer shell, an octet. And it takes energy to move an electron, so atoms will always move as few as possible. That's why any element found in family 1, 2, and 3 will lose their electrons because the outer shell is now gone and the next shell in was full. And any element found in family 5, 6, and 7 will gain because they have less electrons to gain to bring in to fill their outer shell. And of course, family 8 doesn't need to gain or lose electrons. It doesn't need to, it already has a full octet. And in family 4, the carbon family, it's equally available to gain or lose electrons, and so it kind of depends on the nature of the elements around it. The only thing we can do differently in grade 12, as far as those representative elements are concerned, is I can tell you exactly which electrons are gained and lost. In the case of sodium, the electron configuration for sodium as an atom ends at 3s1. It has 1 valence electron and 1 dot. If I were to draw an orbital diagram for sodium, I have two electrons in the 1s level, 2 in the 2s level. We fill in 6 in 2p and 1 in 3s. This is my valence shell. There's only 1 electron there. So what sodium does is it loses that 1 electron. By doing that, the next shell in is now a complete stable shell. Because we have lost 1 electron, this electron was removed. The charge is now +1. In the case of chlorine, chlorine had filled in 3s2 and 3p5. Again, if you look at the orbital diagram for chlorine, you will see that we have 7 valence electrons filled in. The ones with the highest principal quantum number are our valence electrons. In this case, it was less work to bring in an extra electron and fill this in to be 3p6. So this is the electron configuration for the chloride ion, and it will have a -1 charge because we've added an electron. So this is exactly the same as you've been learning all along. It's just now I can tell you exactly where we took the electron from, and also where we may have added an electron in the case of forming an anion. So why are we bothering to show you this? Well, this understanding of my electron configurations and my orbital diagrams actually allows us to explain what's going on when transition metals form ions. So let's take a look at a couple of different transition elements and explain how they form ions. Let's start with iron. When we do the electron configuration for iron, and if you take a look on the periodic table to help you see what's going on, you'll find this helpful. In period 1, we have 2 electrons, so that's 1s2. And then we fill in 2s2, and I'm missing the number 2p6 here in our electron configuration. Then we have 3s2, 3p6. We then filled in 4s2 and then 3d for 6. So my valence shell was just this one. This is the one with the highest principal quantum number. And this is my valence shell right here. Now that's actually going to be further from my nucleus. So those are my furthest out electrons. But the 3d6 kind of matters. So since 4s2 is my valence shell, those have to come off first. They are the furthest ones from the nucleus. And those electrons are spinning around that nucleus very quickly and almost act like a shield to the inner electrons. So if I remove my 2 valence electrons, you notice that in this example they are gone, I've removed 2 of the valence electrons. I will now have iron with a +2 charge. But that leaves us in an interesting scenario, because now iron will still have 1s2, 2s2, 2p6, but it will have 3s2, 3p6, and also 3d electrons with 6, which is what you're seeing here, those 6d electrons. And this is kind of an unstable scenario. Remember, my d subshell has the most stability when it's empty, when there are 0 electrons in it. When it's exactly half full, so when there are 5 electrons in it, or when it is completely full, when there are 10 electrons in it. So we can actually pull electrons out of the d subshell now, because now it's exposed and is sitting in the outer parts of the atom. So I can now lose one more. I've lost these 2 already, and now I've lost one more, so now I've lost 3 electrons. And so iron could also have a +3 charge. So of the 2, iron with the +3 charge is actually more stable because the 4s sublevel is empty, and my 3d sublevel is at one of my stable configurations. Now, having said that it's more stable as an ion doesn't mean that it's necessarily more common. Both iron +2 and +3 are available, and once they've bonded to an anion, they become stable in their bond. But it is the more stable of the 2. So how would I explain copper? Well, when I fill in the electron configuration for the copper atom, we actually end up with an interesting scenario. Following the off-bar rule and going in the order that we see them, we would end writing copper with 4s2 and 3d9. And of course, we remember that if we have 3d9, we can electron promote and bring one over. So this is copper as an atom, but we know that more likely what will happen is we'll move that one electron over, and this is also copper as an atom. So this is not an ion. In both cases here, this is copper as an atom. What happens when we form an ion? Well, you have to remember that according to quantum theory, we're not saying that this electron is always here all of the time. We're just saying that it is mostly here most of the time. So this is probability. We'll probably find it here more often, but not always. Electrons can move. So if the electron was over here, and we were at 4s1, 3d10, and we lost that one electron. We lost this one electron to get this scenario, 4s0, 3d10. We have now lost only one electron, and we have copper with a +1 charge. But if that electron had been in this position when they were ripped off by an anion, because remember, these electrons don't just fall off. A stronger atom has come along and pulled them away. If the electron was over in this position, then we could have lost both of them because they both would have been further from the nucleus. We could have lost two of them. We would be at 4s0, 3d9, and this is copper with a +2 charge. So this again is the more stable of the two, not necessarily the more common, but because we have the availability to electron promote, we can have more than one charge. So I'd like to do another quick example with you. Let's try and take a look at a case like scandium. And we know that when we're doing scandium, which is at the middle of our fourth period there, we can see that after argon, we filled in all of the elements up to argon. We would fill in 4s for 2 and 3d for 1. So let's see how that would look. Here's my 4s subshell, and it's got 2 electrons in it, and my 3d, which is slightly closer to the nucleus but higher in energy, and it has 1. So I can lose first my valence electrons. There's no availability to electron promote here. I can only ever promote 1, and I only do that if I end on d4 or d9, so that's not a possibility. But I could lose both of these, and once I've lost both of those, I'd have scandium, who'd lost 2 electrons and therefore has a charge of +2. But it's also possible now that I could lose one more to become even more stable and have scandium, who has now lost these 2 because they had to be lost first, and then the D, and have scandium with a +3 charge. And we can lose multiple electrons from that D subshell. If we move over just one more to titanium, we see that for titanium, the electron configuration ends at 4s2, 3d2. So my orbital diagram has the 2 electrons in the 4s sublevel. And in the 3d sublevel, you'll see these 2 electrons. So titanium could first lose these 2. Again, you have to lose your valence first to give me the scenario of 4s0, in which case titanium has a charge of +2. Titanium can then start losing the 3d electrons. If it loses one more, I've lost a total of 1, 2, 3 electrons. And it can lose still one more and become +4. And in the D subshells, you'll quite often notice that these D electrons can be pulled off one at a time, and all these possibilities exist. And this is something that only exists with D subshell electrons, which is why our transition metals have multiple charges available to them. In the case of titanium, of all of these, the most stable would be titanium with a charge of 4. because we're at 4s0 and empty, half or full is stable. And we're at 3d0 and empty, half or full is stable. So this is all at a stable configuration. So what I'm going to get you guys to do is reading about ion formation in a couple of places in your textbook, chapter 5.2 and 7.1. And there is a few questions for you to do in each chapter to practice what we've seen with drawing Lewis dot diagrams for atoms and also figuring out the possible charges that would form for ions.